The aspirin question. This is, again, a very classic question, which is why it's here. You could just almost do this for any molecule. We did something like this. Which set of hybrid orbitals best describes the AB bond in aspirin? So between here and here, okay? Let's see if this works. Okay, that carbon, maybe I'll do it like this. Carbon B has what hybridization? sp2, because there's 3 groups, double, a single, and a single. And oxygen A is, there's a number here, 3. Lone pairs, remember? Every oxygen has 2 lone pairs. Always think, how many lone pairs am I looking at here? If it's a non-carbon, it has lone pairs. Okay. What set of hybrid orbitals best describes that bond? It will be I don't know how I wrote it in the answer, I'll have to look, but essentially it's the overlap of the sp2 from carbon with the sp3 from oxygen. So those orbitals, literally the orbitals that make that they have, those make the bond. Okay, what's the approximate bond angle of oxygen A? What do you think? Yeah, how did you know it was 109.5? Because there's 4 groups. 4 groups means tetrahedral, and tetrahedral means 109.5. Okay, C. What is the bond order of the AB bond? I don't know, I see 1, so I'm going to go with 1. Is that okay? It's 1 bond. No clear resonance that is as good as this structure. So I would just go with 1 because it's a single bond. Okay, who's next? Great question. Yes? It's also this worksheet. I'll borrow yours so I don't steal anybody's. There you go. This is 23, the one in red, that number right there. Oh. Yeah, I see why you say that. The BH3, there's a BH3 question, number 23. Good point. We probably wouldn't ask you the oxidation state of that, but we would ask you all other questions. Yeah, that one gets a little dicey. Great question. Okay, next, up here in the front. Yes? If you're not in my class, you have no worries about the practice finals because the 4 that are in here are also posted by your instructor. So we're all posting the same finals because we have a common final and give you the same experience. But I just do extra worksheets. So that's why there's an extra final in here and extra sample questions. I mean, I guess if you really want to get this, you can. It's also on reserve in the library. So you go there. Yeah, that's about your only hope. Okay. But what you have from your instructor is definitely sufficient. Yeah. Okay, next question. What, 15? Okay, this is number 15 on final exam winter 07. Number 15, final exam winter 07. Here we go. Yes? This is what was wanted, right? Okay. I see wavelength associated with an electron traveling at a speed. So we got velocity. It happens to be the 10th the speed of light. So whenever I have a wavelength and a velocity, this is looking like de Broglie to me. De Broglie is, it's on the back of the exam. Let me see if I can remember it. It's H over mu. There we go. So whoever asked this, we're solving for this. This will be in meters. These are SI units. This is Planck's constant. This is the mass of the electron. Where would you find that, anybody? Back of the exam. And this velocity is right there. 1/10 c. C is on the back of the exam. It's the speed of light. Is that okay? It's a big clue that you're going to use de Broglie anytime you see a wavelength and a velocity. Wavelength and velocity together, it's the de Broglie equation. That's the only equation that combines those two. Okay, who's next? Yes. SOF4. Did I get that right? Okay. Here is a made-up question from the audience. I love that. SOF4. Right? Okay. All right. Nope, we can't see it though. There we go. Valence. Okay, well, let's just start with this. Valence electrons, sulfur's in column 6, oxygen's in column 6, fluorine's in column 7. Wow, what does that add up to? 28 and 1240? Okay. The way you stated it makes it a little harder to know what's the center atom. Is this the way it was given on the worksheet, or did this come out of your imagination? Oh, it was from the AL homework? Probably, if this was an exam, I would have written it like this, unless I wanted to make this exceedingly difficult, which is fine. I like that. I probably would have written it like this, to indicate that the sulfur is the central atom. It's kind of tough to do it without that, but there is potentially an option that's not correct when you write it like this, which could be a little confusing. The sulfur should be the central atom, and then the oxygen's next. So sulfur surrounded by fluorines, and then an oxygen. This is the most likely structure. That's why on the final I'd probably write it like this, like a typical question. Okay, so let's do the bonds here. 2, 4, 6, 8, 10 of 40. Now let's just go around. 10, 12, 14, 16, that has an octet. 18, 20, 22, that has an octet. 24, 26, 28, that has an octet. 30, 32, 34, that has an octet. Gosh, I forgot. 36, 38, 40, that has an octet. Okay, sulfur breaks the octet, but we're okay with that because sulfur is below the carbon row, so it can have an expanded valence shell. All right, what's the formal charge, anybody, on the fluorines? 0. They're all 0. It's column 7, and I count 1, 2, 3, 4, 5, 6, 7. Doesn't matter which one you look at. So 7 matches 7. How about the oxygen right now? -1. You'll count 1, 2, 3, 4, 5, 6, 7, but it's in column 6. And sulfur right now, +1. It's again in column 6, but you count 1, 2, 3, 4, 5. Let's fix that, because if we can get all 0 formal charges, we win, you know, essentially. So, what atom will I take the electrons from? Definitely the oxygen. Usually the one that's different, and often oxygen is a good one to do that for. Okay, oxygen now has a formal charge of 0, and so does sulfur, 0. So we're good. This is the structure. Do you want me to do VESPR or anything, or you're good? Okay, cool, next. Yes?
Would you consider the one that you just drew with +1 and -1, would you consider that a resonance structure?
Yeah, the one that I had before I drew what's in brown right there, the double bond, that would have been a possible resonance structure, you're right. And if I asked for you to draw all possible resonance structures, reasonable resonance structures, you could have drawn that one. But the best answer is definitely this one. Yes. Usually looking for 0s, and often you can get all 0s or close to it. Back there, yes. Okay, just real quick, did anybody else have a question on this before I go on? Yes? What's the threshold when you can stop breaking the octet rule? That's a hard question to answer, so you don't have to worry about it in this class. But you'll eventually get too many electrons on something. That's something you probably have to wait until Chem 124 to tackle. Any other questions on this before I go on? Yes? How do you know what the central atom is? In my class? In my class? Okay, what I like to say in my class is you're going to look for an atom and then a list of atoms, meaning an atom that has a subscript. See how the F has a 4? So that's a list of 4 atoms. F, 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 and F. That's kind of discouraging. But there's 4 fluorines, okay? So that means the atom before it is central. And then the 4 fluorines, the ones with the subscripts, that's around it. And then the next atom, then you might have to think a little bit where it goes. A good guess is on the previous central atom. So central atoms connected to central atoms. So that's why I put it on the sulfur. When can an atom break the octet? Anytime it's below the row that has the carbon in it. Okay, I'm going on. Yes, where's that person? Yes, what's the final exam? 2009. Do you have a page number?
101.
101. My practice exams. Let me flip there and then see. What number?
Number 30.
30. You're looking at this, right? Okay, this is a style question. It's fall 2009, number 30. Do you want me to just go through the whole thing or you have a specific? Oh, okay. So basically what you want to do, each electron is numbered 1 to 12. You want to write the quantum numbers in here. Let's see if I have a pen that can write this small. I don't know. Okay, the first one is done for you just as an example. So electron number 1, let's just look at it. It's a 1s. So the 1 from 1s is here. This is the s, meaning that means L is numerically 0. Now, m sub L is from this number. So if this is 0, that's 0. And then because it's pointing up, it's a plus 1/2. Okay, let's do the next one. Number 2. It's still a 1s, so 1, 0. So if that's 0, this is 0. And now it's just negative 1/2. So all these numbers will vary by 1 at least. Next one, number 3. That's a 2, 0, a 2s. If that's 0, this is 0. And it's pointed up, plus 1/2. 4, almost the same, but it's pointed down. 5, here's where it gets a little interesting. It's a 2p, 2, 1. P is for the number 1. Let's skip the middle for a second. Let's skip the middle for a while. So this is, I'll come back to it, okay? No worries. Plus 1/2, it's pointed up. So all these, 6, now 5 through 10. 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, are all 2p's. Then it alternates pointed up and down. Pointed down for 6, up for 7, down 8, up 9, down 10. Now you'll notice a little bit of crazy because you don't know how the m sub L goes with the electron number. But we know that you don't know. That's the key. So we didn't care the order of the next set of numbers. There's, because this is 1, there's 3 options, a 0, a plus 1, and a minus 1. You could have written those in any order and would have been graded correctly. So whatever you chose to do is totally fine. So I'll just go, it doesn't matter, -1, -1, 0, 0, plus 1, plus 1. This is totally random. The numbers are right, but the order that I put them is random. Okay, and then the final one is not too bad. 3, 0, 3, 0, and then 0, 0, and up, and then down. Good. Yes? Could all of the numbers have been the same for m sub L from 5 to 10? No, you need the -1, the 0, and the plus 1. Those 3 numbers correspond to the 3 different orbitals. So if you're missing one of them, there's 2 issues. One, if you're missing any of those numbers, you're missing a p orbital. That's one problem. The second problem is, according to the Pauli exclusion principle, you can't have the same 4 quantum numbers for any given electron. So you'd be violating the Pauli exclusion principle as well. Yes? The 2p apply to the 3 middle lines. That's right, because the 2p has 3 orbitals. There's 3 p orbitals, px, py, pz, so that's why there's 3 lines there. You'll see, if you look with a magnifying glass, that this space and that space and that space are all larger than those, and that's on purpose. Yeah, that's because these are together, and these are all separate entities. Okay, next, way up there at the top.
So how do you determine M sub L again?
What's that?
How do you determine M sub L again?
M sub L is based on L. If L is 1, then M sub L goes from minus L to plus L, minus 1, 0, plus 1.
You chose the 0 to negative 1 to 1 at random?
And the order that I put them was totally random. That's correct. Okay, I'm going to take one last question. We're kind of over our reservation period. Yes? Oh, okay. This is from, can I show this? Okay. This is from winter 07. Is ethanol a base in solution? Let me write that. Ethanol, what is, it's right there. C2H5OH. Anybody, I'll ask the audience, is that a base? Because I do see an OH there. It's not. What does the OH need to be connected to make it a base? Any metal. If it's a metal, like sodium hydroxide, potassium hydroxide, etc., that's a base. But when an OH is connected to nonmetals, it's actually an acid.